start by taking some questions from the homework. Then we'll talk a little bit more about this same topic. So again, we're going to take some questions from the homework, and then I'm going to just do some more examples kind of from that same set of topics from, stop talking please, from that same set of topics that that you guys watched the video from last time. And we'll take one little baby step forward to talk about solving by factoring, but it's not much of a step. And then that's it for today. Okay, so it's mostly just kind of continuing to work on the content from last time, as I know it's not super duper easy. But before we get started there, I'm going to take some questions from this most recent homework assignment, this homework 2. So if anybody has questions from that, Joe.
Can you go over number 2, please?
Sure.
Thank you.
You're welcome. Okay, so yes, absolutely. When I'm talking about any of these problems here today, I'm going to be kind of referencing, while I do that, this factoring diagram that I had talked about in the video from the previous lesson. So the questions I ask, or the order that I'm doing things in, is all kind of outlined here in this diagram, which I know is like a lot at first glance. I get that. It's not so bad once you've kind of worked through it a couple of times and you're like, oh, I kind of get it. It just, it's just very specific to try to give you a lot of direction. So it looks really big, but it's not that bad. But I'm going to kind of continue to talk about this as I'm doing these problems. I mean, I can't put it on the same page while I'm doing the problems because there's only so much space on the screen or whatever. But I'm going to say a lot of these things aloud, and if you wanted to be looking at this kind of as I'm doing things, that's certainly, a reasonable thing to want to do. Okay, so this first problem, again, the first thing we check for is a greatest common factor. Easy to see in this that there is no greatest common factor because one of the terms is 1, right? From there, we look at the number of terms. This has 2 terms. So let's just write some notes. Okay. So from the 2-term branch, the first thing we look for is the difference of 2 squares. And it should be easy to tell that that's not a difference of 2 squares because the exponent on the variable is odd. Right? To be a difference of 2 squares, we have to have an even exponent there. After we've checked the difference of 2 squares, we're going to look at the sum or difference of 2 cubes. Here, if I look at the variable on the exponent, it's something that's divisible by 3. So very possible this could be a difference of 2 cubes. So we're going to try to do that then. So I'm going to see if I can rewrite this as something cubed minus something cubed. So that first term, 8x to the third, well, I know x to the third is just x cubed, so I can do that part. I also have to worry about the 8, though, right? Well, if I think about that number 8, 2 times 2 is 4, and times 2 again is 8. So 2 to the third is 8. So that's, I want to write as 2x to the third. And then 1, I need to write as something cubed. Well, 1 is the same thing as 1 times 1 times 1, right? So 1 is also, or 1 to the third is also something cubed. Everybody okay there? So this is like my A, and this is like my B. For my difference of 2 cubes factoring pattern, which I'll write down here for you guys again. It was in the previous notes, but since I'm about to use it to do the factoring, I wanted to write it down here again so that it's easy to see what I'm doing. So now I'm just going to fill a and b into the right-hand side of this formula. So when I write a minus b, I'm going to write 2x minus 1. When I write a squared, I'm going to write 2x times 2x, so 4x squared. And then when I do a times b, I'm going to write 2x, because 2x times 1 is 2x. And then b squared, which is 1 squared, which is just 1. So far, so good, Joe?
I have a question about that. So in the original formula at the top, and then what you're substituting, you're taking out the cube. Is that because in the a and the b, there's already a cube, so like they cancel out? Or not cancel out, but they just go away? Or?
So if I look here, this 8x to the third is my a cubed.
Right.
What I need to do is figure out what just a is. That's what I did there.
Okay.
So that I can plug in over here, which has just a's in it.
Okay.
Does that make sense?
Yeah.
Okay. So that's my first step, is to rewrite the 8x cubed as like something cubed.
Right.
That something is my value for a that I then plug into the right-hand side of that formula. Okay. So now that I've finished doing the difference of two squared, or the difference of two cubes, or the sum of two cubes factoring, I need to check these pieces to see if I can factor those anymore. Well, the 2x plus 1 has two terms, but it's linear, right? It's just x to the first. So I know I can't factor that anymore, right? Linear things are as factored as I can get. The trinomial piece came from the sum or difference of two cubes, right? The trinomial pieces that come from the sum or difference of two cubes will never be factorable. So I don't have to actually check that piece either. I know I've done all the factoring that's possible. So this would be my final answer. Let's do another, right? What else do you guys want to see done here? Hallie. 5? Sure. Okay. So again, the first thing we do is we check for a greatest common factor. Now clearly there's not one there, right? Because the first term has only x's in it and the second term has only numbers. So no greatest common factor there. From there we look at the number of terms. There's two terms. So if we go to the two-term branch, the first thing we check for is a difference of two squares. So if I look at this is a difference of two squares because I have, well, possibly anyways, because the variable part has an even exponent, right? So I'm going to try to write this as a difference of two squares. Okay, so if I think about x to the sixth, that's 6x's, right? Everybody agree with that? If I split that into two separate piles, that would be 3x's and 3x's, right? So that means it's going to be x to the sixth is x to the third squared. Because I have x to the third times x to the third. That's 3x's times 3x's gives me 6x's altogether. Everybody agree with that? 64, I recognize as just a perfect square number, right? 8 squared is 64. So here my a is x cubed and my b is 8. So when I apply my difference of two squares factoring pattern, I get x cubed minus 8 and x cubed plus 8. Yes.
So is the formula different if there's a difference of two squares?
No, not really. It's still the same pattern that we used before. Just the A's aren't always just going to be an X, like they were always X's in last chapter. I think I wrote the formula more generally, but here it's
more specific. Okay.
It's fine to still think about it that way.
Okay.
It's still the same thing. Because we made like a substitution from A's to X's or whatever. So it's Hallie.
Will these formulas, like the A squared,
Well, I would kind of hope you have the difference of two squares pattern memorized.
yeah, but like,
The cubes one I would probably give you. Okay. But we still have more to do on this problem, right? So we did the difference of two squares factoring, but now I need to take each of these factors and check to see if I can factor those. So x cubed minus 8 has two terms. So if I'll work down the two-term branch for this, is that a difference of two squares? Definitely not. Why not? The exponent is odd. Very good. So next thing I look for, is it a sum or difference of two cubes? Certainly should be, right? I can rewrite x cubed as x to the third. And I know that 8 is 2 to the third. We just used that fact a moment ago in the previous problem. So like here's my a is x and my b is 2. So using my difference of two cubes factoring pattern, which I'll write down again, I can write x minus 2 times x squared plus 2x plus 4. And I know that the x minus 2 I can't factor anymore because it's linear. And the x squared plus 2x plus 4 I can't factor anymore because that's the trinomial piece that came from a sum or difference of two cubes. So that piece is done. Hallie, so far so good?
yeah.
Okay. We still have to check the other factor though. The x to the x cubed plus 8. So again, we'll do the same checks. It's not a difference of two squares. It is a sum or difference of two cubes. I can write this as x cubed plus 2 cubed. So my a is like x and my b is like 2. So let me write down that sum of cubes factoring pattern. And then we'll just fill things in. So we'll have x plus 2 and then x squared minus 2x plus 4. And again, neither one of those two factors we can simplify more. The x plus 2 is linear. And then the other piece is the quadratic part from a sum or difference of two cubes that we know we can't do anything with.
So you just put, since there were two parts to it, the two parts that you had, you combined them at the end for the final?
Yes. Yeah. Since they were multiplied here, whatever they give me also gets multiplied together. So we just stick those two parts together.
Oh, can I ask one more question too?
Absolutely.
Oh, where'd you get the 4 from the end? Is that part of the, because I can't really read what the end is.
Oh, well, it's the b squared.
Oh, makes
So
sense now.
2 squared is 4.
Yep.
Yep.
Thank you.
That's what you're asking, right?
Yeah, yep.
No problem. No problem. Yeah, I guess that 2 got kind of squirrely looking. We probably have time for one more if we'd like to do another one of these. If you don't, that's okay.
Can we do 3? It seems like it's people.
Sure, we can do 3. So again, I want to say here as I'm doing these, I'm including like a lot of justification that I'm referring to the flow charts on. That's not necessarily things that you need to include in your homework. You certainly can if you'd like to. I'm doing this because these are like notes, and it's kind of helpful to so you know what I'm kind of thinking as I'm doing these problems or what I'm checking. So just as a heads up, right? So again, 64x cubed plus 125. The first thing we'll check for is the greatest common factor. There isn't one, right? Since 64, all of its divisors are factors of 2, and 125, all of its divisors are factors of 5. So nothing in common there. This again is 2 terms. First thing we look for is a difference of 2 squares. Obviously not, since it's an x cubed on there. Next thing we look for is a sum or difference of 2 cubes. So we're going to try to write this as something cubed plus something cubed. So obviously the first piece has got to have an x in it, right? Because we have an x cubed. Now, can I write 64 as something cubed? Well, 4 times 4 is 16, and 16 times 4 is 64. So I can write 64x to the third as 4x cubed. Everybody's okay there? 125, can I write that as something cubed? Well, 5 times 5 is 25. And 25 times 5 is 125. So that is 5 cubed. So my A is 4x. My B is 5. So I'll use my sum of 2 cubes factoring pattern, which again, so A plus B is 4x plus 5. A squared is 4x times 4x, so that would be 16x squared, minus A times B, so 4x times 5 squared, or plus B squared, which is 5 squared, which is 25. And term and the piece that came from the quadratic that came from the sum or difference of 2 cubes, neither of which can factor anymore, so that would be the end of that problem. Does that feel okay there? Yeah. Again, going through and using the chart really makes a big difference, or knowing that that's really what you need to be using. Megan.
So what are the tips on how to know whether it's practical or not?
So basically what we're doing is, if we go back and we look at this diagram, if you get to a stop, that means that piece is no longer factorable, whatever it is you were trying to work on. So that's our indicator that whatever the part of it, or even the whole thing, if you're still working on the most outer part, is no longer factorable. Is that what you're asking?
How to just tell right off the bat if it's factorable or not?
Okay, so there's linear things. If it's just x to the first, that's the biggest degree thing. Those are all done, right? Like if you run into a piece in your factoring that's linear, you can't do anything more with that, because at that point you would have already taken any greatest common factors out. And the other part that I've used a bunch of times, these trinomial parts that we get, those parts are also always are not going to be factorable anymore, provided that you've been using the framework that we've outlined here. It is possible that those parts are factorable more, but not if you're using the diagram the way I've outlined it. So the place where you could run into trouble is if you had something like number 5 here, that you could have also done as a difference of cubes. If you did the difference of cubes before the difference of squares, there you'd end up with that part at the end being factorable, but there's no good way for you to deal with it. So you did do that?
Yeah.
Okay. So that's why it's critically important when we're using the diagram here, that when we're doing the two-term stuff, that we always check for a difference of two squares before the sum or difference of cubes. So as long as you do that first, the quadratic parts from the sum or difference of two cubes are going to be done. You won't have anything more to do there. Does that feel okay, Megan?
Yeah.
That's what you're looking for? Was that kind of a conversation?
Yeah.
Okay.
Yo, Mr. Cooling.
Yo.
So do number 6.
Okay.
Thanks.
Yep. All right. So 6, again, easy to notice there's no greatest common factor, right?
Yeah.
Because one of the terms is 1. So I look at this and I know that we have two terms. The first thing we look for is a sum or difference of two squares, which we have, right? Or at least potentially, because we have an exponent and then a minus sign. So at least we're in the right format. So x to the 8th is 8 x's. I divide it into two pools, so it'd be 4 and 4, right? So it's going to be x to the 4th squared. And 1 is just 1 squared. So like my a is x to the 4th. So when I do my 1 plus 1. So far so good, Ben? Now I need to check each one of these. So the x to the 4th minus 1 is two terms. So the first thing I check there is the difference of two squares. Well, it is, right? So I can write minus 1. Then I need to check each one of those results. So we'll start. That's also a difference of two squares. Plus 1, right? Now we'll do x squared plus 1. That's not a difference of two squares. Notice why not? The x squared plus 1 is not a difference of two squares. Why not? What? The mask and the mumbling, I couldn't.
Because you're already at 2, you cannot go down anymore.
It's because it's an addition problem. Right? A difference of two squares has to be subtraction. This is addition. So no, it's not a difference of two squares, right?
Yeah.
Okay.
So let's start writing our answer out. So we have this piece. We still haven't checked x squared or x to the 4th plus 1 yet to see if that can be factored. So let's go back and do that. Is that a difference of two squares?
Is that plus 4 or minus 5?
It's x to the 4th plus 1
Oh.
is what we're looking at. Is that a difference of two squares, though?
Yeah.
No. Why not?
Because it's addition.
That's because it's addition. So for we're going to continue doing some factoring by polynomial practice.
Alright, Zach, that's no. Zach, that's no.
So we'll do like 3 examples again of this. Same thing that you're doing last night. And then we'll talk about solving by factoring, which is just a teeny little step forward. Okay, so we have 4x to the 5th minus 16x to the 3rd minus 180. The first thing we check for is a greatest common factor. In this case, what is our greatest common factor going to be?
4 or 2.
Okay, so you said, I heard somebody say 4. If I look at the coefficients, 4 divides 4, 4 divides 16, and 4 divides 180, so we can take out a 4. But don't forget about the variables, because it's more than just 4 that we can take out as a greatest common factor. 4x, right? So when I take out the 4x, I have then an x to the 4th minus 4x squared and a minus 45. Is everybody okay with what we did to there?
Yep.
Okay. So the 4x, that greatest common factor, we're just going to kind of ignore from now. It has to come with us on every step of the problem, but we're done kind of doing anything with it. It just kind of hangs out front for the rest of the ride. The part that we're going to talk about from here on is going to be the x to the 4th minus 4x squared minus 45 part. So when we look at that, we're going to look at the numbers. That's the. How many terms do we have there? 3. Okay. So if you look at your factoring tree, the 3-term branch, the first thing we look at is we ask, is it in the quadratic form? So to tell if something is in the quadratic form, you need to do 2 things. Your biggest exponent on the variable has to be twice as big as the other exponent on the variable, which we have, right? 4 is twice as big as 2. And the last piece has to be a constant, which we have. Everybody's okay with what it means to be in the quadratic form? Okay, so that's yes. After that, since we're in the quadratic form, we want to look at whether the leading coefficient is 1 or not. In this case, x to the 4th minus 4x squared minus 45, is the leading coefficient 1?
Yeah.
Yes. Which tells us we can do the shortcut factoring. So we just need to find the 2 things that multiply to give us negative 45 and add to give us negative 4, just like we did when we factored quadratics. What are the 2 numbers that work? Multiply to give us negative 45, add to give us negative 4.
9.
Negative 9 and positive 4, right? Or positive 5, excuse me. Everybody agree with that? Okay. Now, just as a little aside, if we factored x squared 45, we would write just x minus 4, x plus, or x minus 9, x plus 4, 5, right? Everybody agree with that? Here, though, it's a little bit different. So it's still going to be something minus 9 and something plus 5. The difference being that instead of an x, we're going to have an x squared, because that middle term, the variable, is an x squared instead of an x. Is that okay with you guys? So that's an easy thing to forget to do, but it's really important that you do that. Now we're just going to check each of these factors and see if we can do anything more with that. So this one is two terms. So the first thing we do is we check for a difference of two squares. Well, that's a difference of two squares, right? That looks just like a first semester factoring problem that we would have done. So for the x squared plus 5 now, is that a difference of two squares? Definitely not, right? For two reasons. One, it's addition. And the other, 5 isn't a perfect square, right? So two good reasons where you could have said that. So then we move on. Is it a sum or difference of two cubes? Definitely not, right? Because the exponent on the variable isn't divisible by 3. So there's nothing more we can do with that. So we're done. Oops. We forgot about the 4x. 4x has to still be out front. Now we're done.
You just carry the 4x.
Yep.
The whole problem.
Yep, you just carry that 4x the whole way through. Whatever you're doing, that 4x just stays out front, doesn't change, doesn't go anywhere, doesn't combine with anything. Does that feel okay? Hopefully this is starting to feel a little bit easier as we're doing some more of these examples. Yeah. You're saying, what if you just left this answer?
Yeah.
Well, the directions say factor completely, so that would not be full credit, because there's still more factoring you can do, specifically the x squared minus 9. Does that make sense?
Yeah.
Okay. So it's not like it's all the way wrong, but it's just not finished, right? So let's do another example. Okay. So we have 2x to the 7th plus 6x to the 5th minus 16x to the 4th minus 48x squared. Again, the first step is to look for the greatest common factor. In this case, what's the greatest common factor?
2x.
Well, 2x squared, right? Because all the terms have at least an x squared in it, right? Everybody's okay with that? So when I peel that off, oops, I have this. Everybody cool? Okay. Again, we ignore the greatest common factor for now, and we're just going to focus on this piece. Looking at the number of terms, how many terms do I have there? 4, right? So when I look at my 4-term branch, the first thing it asks me is to try factor by grouping. So the way we do that is we're going to make 2 groups. We're going to group the first 2 terms together. And then we're going to group everything else together. But if you remember, when you do this factor by grouping, you have to have a plus sign in between your 2 groups. Since I had a subtraction symbol there, I just wrote it as like plus a negative and stuck the negative sign inside the other group. You guys see that? That happened in first semester that we had to be careful about, right? Okay, so continuing with our factor by grouping, now that we've made our two groups, we're going to take a greatest common factor from each of them. From the first group, we can take out a greatest common factor of what? X cubed, good. And that leaves us with x squared plus 3. And from the second group, what can we take out? Negative 8, very good. And that leaves us with x squared plus 3. Now, what we're looking for is for those two parts to be identical, which they are. This tells me that we can continue our factor by grouping. If these two parts were not identical, and we checked to make sure we didn't make a mistake, and we didn't, at that point we'd be done. There's no more factoring to do, so the last answer we had would be our final answer. There, all we could have done was take a greatest common factor out. But we can do more in this case, since those two pieces that I highlighted are identical. So I can take out that x squared plus 3, I'll factor that out, and that leaves me with the x cubed minus 8. Now I need to check each of these factors to see if I can do more. So the x squared plus 3 has two terms. First thing I'll check, is it a difference of two squares? No, right? Because it's addition, and also the 3 isn't a perfect square. Then we check, is it a sum or difference of two cubes? Well, no, can't be that either, because the exponent is 2. It's not a multiple of 3. So that first part is done. So if we start writing our answer out, we know the 2x squared is there. We know the x squared plus 3 is there. Now we'll move on and start worrying about this x cubed minus 8. Is it a difference of two squares? Definitely not, because the exponent isn't even. Is it a sum or difference of two cubes? Yes, right? And this is actually one that we factored before already in the homework, or in the exam homework from yesterday. Do you guys remember doing this? So if we go back and check here, where did it happen? It happened right there. Right, we already did x cubed minus 8. See that? I highlighted it there in yellow. During that problem, we already factored that thing. This was the result. Well, I'm just about to shortcut something. I'm just referencing you why I'm going to shortcut something. I'm just stating that we've already done this problem that we're running into again. So I'm just going to point out how I'm about ready to write down this next answer without having to do any work. That's all I'm doing. Is that okay, Hallie?
Yeah, that's fine.
Okay. So that's all I did there, is I'm just going to shortcut. Oops. Here. And just copy that answer that we got before. And I know that the results from that can't be factored anymore because I had a linear piece, the x minus 2. And then the quadratic piece came from factoring a sum or difference of two cubes. Okay, Alexis, where did I lose you?
I get everything else, but I need the x minus 2.
No.
Oh. But I don't get like x minus 2, x squared plus 3x.
So I skipped a bunch of steps because we did this specific problem up there where I did all the work for it. So in the interest of time, I just skipped showing all that work because we already did the problem on the same sheet of paper and the same homework assignment. So I just said I'm going to copy my answer from up here. Is that what you're asking? Okay. Do you understand where I got my answer from down below? That I just copied it from here, right?
Yeah, I understand.
Okay. Do you understand how I got the answer here? Okay. So there is a factoring pattern that I'm using right here for the difference of two cubes. Okay, that was in the notes yesterday. We had to use it, I think, in almost every one of the problems in that homework assignment from last time. So what I did is I rewrote x cubed minus 8 as something cubed minus something cubed. So x cubed is just x to the third. 8 is 2 to the third. So that tells me my values for a and b, which I then plugged into the right-hand side of this thing to get the a minus b is x minus 2, a squared is x squared, ab is 2x, b squared is 4. Does that make sense now? Okay. And just FYI, the sum formula is right next to it. There. Also was in the notes yesterday. Okay.
Does it plus
Okay, which formula? On the one on the left or the right? So it's a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. Uh-huh. Okay. So let's talk about solving by factoring now. It's not much of a step forward, it's just a little teeny baby step forward. But we're just going to add in some more skills that we developed in first semester that we already know how to do. Okay, so I'm going to just scroll down. So the main tool that we're going to be using here is, once again, this zero product property that states if a times b is equal to 0, then a equals 0 or b equals 0. And the way we used this in first semester was we used it to solve a problem like x squared plus 9x plus 18 equals 0, which allowed us to write that as, like, we could factor that into like x plus 6 times x plus 3, and then we could take each of those factors and set them equal to 0 and solve them separately, right? You guys kind of remember doing that last semester? Okay. We can use this exact same plan of attack to solve polynomials by factoring. So in the interest of time, because I'm want to make sure we have some time to do some examples here. I'm going to go back and use these previous two examples that we just factored. I'm going to like rewrite them as solving problems. I'm going to borrow all the work that we did to factor them to shortcut to the factored form, and then finish up the solving part, just so we can worry about the solving part in these examples without having to worry also about the factoring piece. So notice this is the exact same polynomial as the example A for factoring. Everybody's okay with that? So the first thing we do is factor. So I'm going to steal this work to just write this in the factored form. Okay there. Now, if this is a fresh problem, you'd have to do all that factoring still before you got to this point, or to get to this point. But since we're really just trying to worry about the solving part right now, I'm going to just shortcut through all that factoring because we already did it. What I can do now is I can apply that zero product property and take each of these factors and set them equal to 0 and solve each one of them separately. So 4x is equal to 0. I'll divide both sides by 4. I get x is equal to 0. X minus 3 is equal to 0. I add 3 to both sides. I get x equals 3. X plus 3 is equal to 0. I can subtract 3 from both sides to get x equals negative 3. And then that last piece, x squared plus 5 is equal to 0. That's a quadratic, right? We talked first semester, there was 3 ways to solve quadratic equations. You can solve it by factoring, you can solve it directly, or you can use the quadratic formula, right? Now, in a case of solving a polynomial by factoring problem, you're not going to be able to factor the quadratic piece that's left anymore, or else you would have had to factor it in the factoring part, right? If that quadratic was going to be factorable, we would have factored it while we were factoring the polynomial. So we're not going to be able to use factoring really as a solving part for these quadratic pieces. So it leaves us with solving directly or using the quadratic formula. Remember, the quadratic formula we can always use. Solving directly we can use only in the situations where we have only x squareds, which is what we have here, right? We just have a problem with an x squared in it. So I'm going to use solving directly, although you could still use the quadratic formula. I think directly is a little bit easier. So I'm just going to subtract 5 from both sides and then square root both sides. Because I square root both sides of the equation creates a plus or minus. Because I'm square rooting a negative, that makes an I. And then the square root of 5 I can't do anything more with because 5 is a prime number. So there's my answer to that piece.
That's it?
That's it.
It's not that bad.
Not that bad. Marco.
Can I use the restroom, please?
Yes, sir. Okay, let's do the next one. Right, what was our other one? So again, we're going to take that same problem that we just factored, 2x to the 7th plus 6x to the 5th minus 16x to the 4th minus 48x squared equal to 0. And we're going to solve that. So again, the first step is to factor it.
That's the hard part.
That is the hard part, absolutely. Yes, if you can get through the factoring part, the solving part should be fairly easy in comparison. That's why we're calling this just like a tiny step forward, right? Because the solving parts is just turning into a bunch of problems that we were able to do in first semester. Yes?
What's the first?
Yep. So now now that we factored, we can use that zero product property to set each of these factors equal to 0. And then we can solve each one of these. I'm just going to solve this one directly. Now notice that even though I square rooted both sides and I get a plus or minus, the square root of 0 is 0, so plus 0 and minus 0 is still just 0. So that's why there's no plus or minus in this problem, for that part. Here, again, this is just like x squared plus 5. I'm going to just solve this directly. So far, so good. This one will just add 2 to both sides. And the last one is a quadratic, but this quadratic has both x's and x squareds. So we're going to have to use the quadratic formula on this piece. Okay, so let's see. 2 squared is 4, minus 16 is negative 12. So we're square rooting it. And note that 12 is 4 times 3. So the square root of 12 is the square root of 4 times the square root of 3. And the square root of 4 is just 2. So I can rewrite this as negative 2 plus or minus 2i square root 3 over 2. And then I can reduce this by writing this as 2 separate fractions. So negative 2 over 2 plus or minus 2i root 3 all over 2. So negative 2 divided by 2 is negative 1. 2i root 3 over 2, the 2's are going to cancel to leave me with just I root 3. And there's our best answer to that piece. As an aside here, for you guys, I would still accept this answer here. If you had given that to me, I wouldn't have marked you down for that. But keep in mind that on a standardized test like an ACT or something, they wouldn't have, your answer would look like this one down here. So just FYI. Okay. So I'll pause here for a minute. I see people still kind of writing, trying to catch up, and I don't want to hurry along and leave a bunch of people behind. Yes, Joe?
Is the reason why you use the quadratic formula because there were 3 terms, or what was up? That's why?
Yeah, since there's x's and x squareds.
That's why.
Yep. Exactly. All right, so we're going to do one more problem, example problem here together. So I'm going to write it down, give you guys, like 5-10 minutes to work on it, and then we'll go through it together, and that'll be the last thing we do today. Sound okay? All right. Okay, so you're going to solve this by factoring x to the 6th plus 26x to the 3rd minus 27. Take some time, work on this on a separate sheet of paper. We'll take 8 minutes. At the end of 8 minutes, regardless of where you guys are at, we'll go through it together. Do as much as you can in that time. do the best job you can do in that time. This isn't an assignment, it's not to turn in, just do it in your notes or on a separate sheet of paper, just kind of a self-check to help you get a better handle on these concepts. It really helps to try some on your own before you have to do the homework to get some immediate feedback. You know what I mean, guys? And then we'll go through this together as a group at the end of 8 minutes. That should be a good chunk of time to where you can make some progress here on it, if not finish it. Okie doke. I'm going to stop talking and let you guys think.
Sure, cool. Can I ask a question?
Yeah, go ahead.
How can you tell if the quadratic formula is in the problem? Does that make sense? I don't know how to ask it.
Oh,
I'm looking at the steps and like.
so that's quadratic form, not formula.
Okay.
Yep. So that you look at whether the degrees, the exponents on the variable, the biggest one has to be twice the smaller one,
Okay.
and then the last thing has to be a constant, which is what we have here, right?
Exactly.
Yep.
And then since the leading coefficient is 1, we can do this.
Yes, sir. Yes,
Can I
sir.
come up and ask you a question?
Sure.
Alright, I think I did these steps correctly. Come into here.
Good.
But when you do the two terms thing and the difference or the sum, since it's a cube, it's not like the squared one, right?
Right.
So then I'm forgetting what.
So you want to write as something cubed minus something cubed.
Okay, so something cubed minus something cubed. Sorry.
Yep.
Cubed. And then so over
x
here.
cubed is just x.
Right.
Can I go to the bathroom?
Yes, sir.
And then for something cubed over here, 27, that'd be 3. And then, so just keep it like that pretty much?
Well, so then you can use your factoring pattern for the difference of two cubes, where this a is x and b is 3.
Oh, and then I put it into the formula?
Yep.
And then I do the same thing for this?
Exactly
one too?
right. Yes.
Okay, thank you.
Yes, sir. Okay, let's get ready to roll here.
Yes, sir.
So that's been about 8 minutes. There's no greatest common factor. It's got 3 terms. It's in the quadratic form because the biggest exponent is twice the smaller exponent, and the last number is a constant. The leading coefficient is 1. So we can use the shortcut. So we need to find 2 things that multiply to give 27 and add to give us positive 26. That's 27 and negative 1. So that's going to let me go straight to x cubed plus 27 times x cubed minus 20 or minus 1. Then I need to check each one of those. They're both 2 terms. They're not dots, but each one of them is either a sum of 2 cubes or a difference of 2 cubes. So this first one I can write x cubed plus 27 as x to the third plus 3 to the third. So my a is x and my b is 3. So when I apply my sum of 2 cubes factoring pattern, I would get x plus 3, x squared minus 3x plus 9. And similarly here, also a difference of 2 cubes, where a is x and b is 1. So when I fill those in, I get x minus 1 times a squared plus x plus 1. And all that stuff is equal to 0. I know that's fully factored because the linear terms, or because what I have are linear terms, and then the quadratic pieces are from the sum or difference of two cubes. So I can apply the zero product property to set each of those pieces now equal to 0 and solve them each separately. So the first one I can just subtract 3 from both sides. The second one I need to use the quadratic formula. So let's see, negative of a negative is positive. 3 squared is 9, minus 36 is negative 27. Square root of a negative, we make an I. 27 is 3 times 9, so the square root of 9 is 3. So there's that. Add 1 to both sides there. And again, another quadratic formula. Square root of a negative makes an I. And we're done there. Okay, so a couple of things here I want to point out that we maybe have noticed while doing these last couple of examples. First thing, when we've had to use the quadratic formula to solve these quadratics that are left when we do the sum or difference of two cubes, notice every time we've got an imaginary answer, right? That's always going to happen. So if you have to use the quadratic formula to solve one of these quadratics from the sum or difference of two cubes, you should be getting imaginary solutions to all of those. Okay. That doesn't mean that every time you solve a quadratic, you're going to get an imaginary solution. But if it's one of these pieces that come from the sum or difference of two cubes, it will be imaginary. But the solving part here at the end is essentially just turns into a bunch of first semester questions, right? So the hard part is getting the factoring done correctly. If you can factor it correctly, from there it should be relatively easy in comparison. So for next time, what I'd like you to work on is this homework 3 that's in the content library. I have 5 questions where I ask you to factor completely. And then I have 5 questions where I ask you to solve by factoring. Okay, make sure you're showing work when you're doing these. Do not just give me a list of answers. I'm going to start being very picky about this semester. By the end of last semester, our homeworks were kind of a joke where we're just having like lists of answers that wouldn't really tell me much when I look at it about whether you know how to do this or not. So I am going to be pretty picky about this going forward. So make sure that you're including some work. Okay? Real work. Okay? As always, if you have questions on things or you get stuck on something or you don't understand something or you want some feedback or whatever, come find me during community time or some other time and ask me. I'm happy to take a look at what you're doing or give you some more advice or insight or re-explain something or do another example or whatever. Okay? Okay. Questions for me about anything else?
Thank you.
Okay, well that's a wrap.